So thanks for coming for the colloquium. So today we have with us Professor Gerardo Herrera Corral, who is a full professor at CINVESTAV in the physics department. He's an experimental high-energy physicist. He obtained his PhD at Dortmund University in Germany, working for the Argus experiment in DAISY. And then after that, he did a postdoc at here in the United States at Fermilab, working with some fixed target experiments. And after that, he did some postdoctoral research also in Brazil. And when he finished that, he obtained his position at CINVESTAV, which is one of the largest research centers in Mexico. And he's been developing this high-energy physics, working different experiments in Europe and the US. And also more recently, he's also involved in medical physics. And this is actually the topic of the colloquium today. Professor Herrera has a lot of distinctions, so a lot of awards that is a big list. I will not mention all of them because I will spend too much time saying all of them, but he essentially got all the most prestigious awards in Mexico and Latin America, and even at some some of his awards are the Fulbright Awards, the Humboldt Award, the awards of the Mexican Academy of Science. He's been Secretary of the Academy of Science in Mexico, Secretary General of the biggest research center in Mexico. So he's been in a lot of, just a few weeks ago, he got one of the very prestigious scientific awards, Chronica and others in Mexico. So we're very happy to have Professor Herrera here to discuss about these projects on medical physics. So please, let's welcome Professor Herrera.
Oh, thank you, Daniel. Thank you very much for the introduction. I hope you can listen correctly. Yeah, thank you very much for the invitation, and thank you for the introduction. I will try to give you a quick view of one of the projects in which we are working in, though as you have already learned, my main research is in high-energy physics. I work in an experiment in the Large Hadron Collider, but I've been trying to do some local projects in CINVESTAV related with applications of the things we do, the detectors, and some of the techniques we use in high-energy physics in medicine. So, and I start with this beautiful picture of a flower, which reminds me also that the X-rays have had an influence in many areas of our lives, and one of them is arts. Since the beginning of the last century, when X-rays were discovered, people started to do images of flowers, and now there are not only people doing this, but they are entering also in the museums. So there are complete exhibitions of art that with pictures like this and some other that are being produced with X-rays. One of those is by Stephen Meyers, who is a guy from Washington. He's a radiology technician and produces these very nice images. In this case, Triumph Tulip is one of them. So you can find some of his pictures in the web, and you can buy them and so on. So there are three reasons why, I would like to start with, three reasons why this colloquium shouldn't be taking place today. So the first one is that in 1886, Pavlovich Puluy published the first radiography. So that last year was 130 years anniversary. So this colloquium should have taken place probably last year to celebrate the round number. But also, October is known as the International Breast Cancer Awareness. So it would be nice to have this colloquium in October, 1 year ago and 1 month ago, so to say. But also should remember that Röntgen, the was credited with the discovery of the X-rays in November 8th. So this colloquium should be taking place probably in 2 days from now. So, and let me probably start with my project that has been for a long time been the main research I'm doing, and this is the Large Hadron Collider, in order to explain why we are involved in things like radiography. This is a picture that you probably know. This is the biggest accelerator in the world. It is called the Large Hadron Collider, and is based in the European Center for Nuclear Research, CERN, in Geneva, in Switzerland. And this machine is used to accelerate protons and make them collide at the largest energy in the center of mass ever achieved. It also collides ions at the biggest energy, as you can see there. And it was in these experiments where the Higgs was discovered some time ago, in July the 4th, 2012. And it was the reason to give the Nobel Prize to these two guys after this elusive particle was finally detected. So this huge accelerator is close to Geneva in Switzerland. You can see the Alps here. And it's a huge machine which is underground. And in this accelerator, there are 4 interaction points where big experiments are placed. One is LHCb, CMS, ATLAS, and ALICE. And my group has been working in this experiment in ALICE for a very long time, 25 years almost. And we have participated in this huge detector that you can see here with the design and construction of these detectors, V0 on one side and Acorde, which is the cosmic ray detector in the upper part of the whole ALICE detector. And recently, in 2015, we also placed a new detector very far away from the interaction point, which is called AD. And it was designed to allow the experiment to do kind of physics which is called in the area of high energy physics as diffractive physics. So this is what we have been doing. We have contributed from Mexico, from our institution, with 3 devices which are part of the ALICE detector. Now one can, in this point, say what all this has to do with X-rays. And let me say that particle physicists have been always very much related with the techniques that are used in hospitals, in particular in diagnostics, but also in therapy. I will not talk about this today. For example, we can start mentioning that when the Large Hadron Collider was proposed in the 80s, people started to worry about how these detectors will cope with the radiation, the intensity of the radiation that was going to be produced if the accelerator become one day a reality. So there were groups that started to develop detectors, and in the 90s, one of these groups started to design and think about detectors with low noise and also with a high capability to measure photons, the high speed. So they started to build and think about technologies and came out with hybrid technology that ended up with applications in medicine. This is called the project Medipix. But originally, these ideas of hybrid pixel technology were applied in one of the experiments of CERN in the beginning of the 90s. It was a fixed target experiment called WA97 that was measuring heavy ion collisions. And it was the demonstrator, the first demonstrator of this technology in integrating pixels in a hybrid way. What this means is that in this new technology, the whole sensor is integrated, embedded in one wafer. This is to say that the sensitive area, which is up here, this sensitive area is together with the readout electronics. In the same wafer, you can find an amplifier, a discriminator, a delay, and a coincident circuit, and even flip-flops. All these integrated in what was called the hybrid integrated circuit technology. This was developed at CERN in order to be able to construct detectors that would have a good performance in the LHC. And this was the first design parameters of those detectors. This was tested in WA97, and this is a picture which is very nice for high-energy physicists because all these red hits that you see, all these red points show the hits where the radiation that was produced in one of the collisions is letting in the different detectors that are placed here. So what you can see is these lines, these blue lines, that match all these points to tracks. And the very nice thing about this picture is that there are no points, there are no red points outside of these blue lines. So this is to say that the noise is very, very low. So this is one of the pictures that we used to show to demonstrate that this technology was very successful. This is a picture of the second version of this chip that used this hybrid technology. Has been already overcome. There is now a fourth, and they are working on a fifth version of this chip. But it's a nice development that physicists were doing in the lab, and that became at some point very, very useful in medicine. And the reason why is because this detector, the detectors before this technique, before the LHC, were able to count up to 100,000 photons per second. And with this new technology, the LHC experiments are able to count 10 million photons per second. So this huge increase in the number of photons that can be measured made possible this apparatus, which is called MARS. MARS is the first X-ray tube, so to say, with a detector that is able to produce radiographies in color. And this is not radiographies in which the color has been superimposed by some imaging processing, but this is true color. This is color that is produced with an analysis of multi-energy photons. So you have that many photons, so such a big flux of photons that you can afford to distinguish photons with different energies and produce different colors for the image, so that one can distinguish here bones from soft tissue and so on. In this, for example, in this radiography that you see here, the bone, which is a calcium, is depicted as a red, and then you see in the cardiovascular system with the blue color iodine, and you see barium in the lung, and so on. So this is the true color produced by the elements that are forming parts of the organs in the body. And this was possible with the technology that was originally designed for the Large Hadron Collider experiments. So there is a strong relationship between what we are doing in the lab as a basic science and things that we can do also in applied physics. On the other side, in Mexico, this is a cut of a newspaper in Mexico. The breast cancer is becoming an issue. So this is just some statistics of the mortality in women in 2008. This is not up to date, but you see the states in the north of the country are having now a huge rate in deaths per 1,000 women, which are older than 25 years, and you see that it started to become a public health problem in Mexico. Before that, in Mexico, we used to have the problem of cervical cancer. But if you look at the evolution from 1980 to nowadays, the cervical cancer, which is with the blue line here, is going down, and then the breast cancer is taking much more importance in terms of the number of deaths that is producing. So these are the numbers in Mexico, the number of deaths per year, and the new cases. But this here, you see the numbers in the world. So it's not only a problem of Mexico; it's a problem of all the countries in the world. Mexico used to be a young country, but people is getting old. If you look at the profile of the ages in Mexico, this was in 1970. It was a country populated by children, But now, 2010, and even now in 2017, you see this population profile goes down here. So it's becoming slowly an older country, and this means that the health problems are changing. So we are having more problems in this kind of issues. For example, in 1990, the women 50 years old were 32% of the population, and we expect in 2030 that this will grow to 61%. So it's going to be an important change in the population. And if you look at the index of aging for 2015, you see how this is growing dramatically. This is the number of adults which are 60 years old or more, divided by the number of children per 100 children and younger than 15 years old. So this is growing quickly. In addition to this, the total fertility rate fell from 7 in 1960 to 2.2 in 2016. So these changes in the demographic population, in the demography of the country, is changing a lot the challenges that we have to face in medicine. Mammography has been a technique which is very successful in reducing the mortality. Some statistics show that this reduces by 50% the mortality, but is far away from perfection. There are many things to be done in order to increase the efficiency of this technique. In particular, the large fraction of false positives is one of the issues. So we decided to do some radiography in CINVESTAV, and this is what I would like to talk today to tell you something about this project. X-rays are coming from many different objects, starting from the sky. I was discussing with Tom that even Jupiter and Mars have emissions in X-rays. There are also X-rays produced in accelerators and many devices that are designed to produce X-rays. There are radioactive sources producing X-rays, and there are new techniques that produce high-intensity X-rays. But we are going to use the traditional X-ray tube. And there are good reasons to think on X-rays tubes because they are widespread. You can find all these tubes all over the country, so you don't need to special infrastructure and big accelerator to produce intensive X-rays if we can manage to improve the technology. So an X-ray, as you know, is just a beam of electrons hitting a target. And when the target is hit, the light is produced by two processes. One is the bremsstrahlung, which is breaking energy that is radiated when the electrons are hitting or reaching the magnetic field of the atoms. And this produces a continuous flux of X-rays that you can see here. This is the continuous energy spectra. But on the other side, from time to time, the electrons hit one of the electrons that are excited, and then this emits X-ray radiation and produce some peaks in the distribution, which is called characteristic energy spikes. In the case of these traditional X-ray tubes, this is a typical spectra that is used for medical purposes. These X-ray tubes have improved since they were invented. For example, in 1912, Coolidge in General Electric managed to separate voltage and current so that one can increase the current and in this way increase the intensity of the X-rays that were produced. And then later on in 1960, there was new technology introduced, which is a rotating anode, and having this made possible to increase the current without damaging too much the anode, which was also one of the limitations, and so on. I would say that the next big improvement in the X-rays is the so-called fine focus technology. The fine focus technology has to do with the spot that is achieved when the electrons hit the target. When these electrons hit this target, there is an area which is called the spot, the focal spot, that produces the X-ray that will be used. And reducing this focal spot is very important in order to get high definition images. So this was the next step, and this is called fine focus technology. This is the X-ray tube that we are using in our lab to produce images, and this is why it is important to have a fine focus source. You have here a very small X-ray source, and you have an extended X-ray here, and you see whether when you have an object, you produce a different image in the plane. So if the X-ray source is very small, then you eliminate, you suppress the shadow, which is this gleam, this how do you say penumbra in Spanish? It's a gleam in English. And this is a blurring. This blurs the images, and does not allow to have a good visibility of details in the radiography. So this is why it is important to have a small source, small focal spot. And in order to do that, there are techniques with magnetic lensing to focus the electron beam as much as possible. So by beam focusing on the one side and a small filament, you can produce a very focused electron beam that hits only a very small area in the target. And this is how you would see the effect of such parameter. You see here an image in microelectronics, which was produced with a source of 10 micrometers for the focal spot. And then when you reduce the focal spot to 1 micrometers and smaller, you see the definition of the image improves a lot. So we are using this X-ray tube, which originally has a copper target, was nominally 100 micrometers in spot size, but we modified the tube, changing this to molybdenum and optimizing the focal spot to smaller value in order to get images of high quality. There is a technique to measure this focal spot. I will not go into these details, but we achieve focal spots of the order of 45 to 50 microns. This is the full width of high maximum, and this is the shape of our focal spot in the tube that we are using. For mammography, the nominal and the wishable, so to say, focal spot is 0.1 to 0.3, so this is much smaller than what is expected for a good mammography in a hospital. And you see for general radiography still larger. So another important parameter of the X-ray tubes is the coherence. And there are two kinds of coherence. One is the longitudinal coherence, and the other one is the transverse coherence length. And this is defined as it is shown here. If you have two waves coming from the same source, if they are slightly different in wavelength, then you take one wavefront here, and you see when this coincides again with the other one, and this length is called the longitudinal coherence length. In a similar way, if you have two waves coming from different points in the source, then they will coincide in one point here, and at some point they will again coincide in the next front, so that this transverse length defines the transverse coherence length. This is an important parameter because it tells you what is the size of the structure that you can define with this X-ray tube. So in the case of our X-ray tube with the new molybdenum target and the beryllium window, we are able to define structures which are as small as 0.7 micrometers. And this is the typical spectra in our tube. So as I said, we have molybdenum, so we have a 70.4 characteristic line, and we have almost 20 keV in the second one. Another important aspect of these X-ray tubes is the hill, which is this uneven distribution of radiation that we have just because of the geometry array. So just because of the angle that the target has, it produces a hill, which is on the cathode side gives you more intensity in the X-rays. So this cannot be avoided. This is part of the X-ray tube, but knowing this allows you to make a subtraction and have an improvement in the images that one obtains with them. We use a commercial detector. We have not modified at all this detector. I will not go into the detail because it's just a shadow box, an old model. It's not even a special kind of detector. It's just a normal one. It uses the technology of indirect conversion. This is to say that the X-rays come from here, arrives to a scintillator, and the scintillator converts the X-rays to light, and this light is then measured in photodiodes, which are CMOS in here. So this is the detector, and this is the dark current that we measure with this. We produce also some phantoms in the lab. We have the ACR 156, which is the accreditation phantom. There is an international standard. But we also produce some other phantoms in order to optimize some of the parameters that we will need in our images. So let's talk about radiographies. And there are two ways of doing radiography. One is the conventional radiography, which is the one we all know. It works with, in this way. You put some X-rays through the object, and you produce a shadow in the plate. So that when the radiation goes through a body, it meets different absorption coefficients, and in the end, you get some absorption that will produce an image. And this is how we have been producing images for more than 100 years. So this is the normal way, the conventional way of producing a radiography. But there is another possibility, which is called phase contrast radiography, which uses not the attenuation, not the shadow, not the absorption of the radiation, but the shift in the phase that is produced when the radiation goes through an object. This is known in the optical. Phase contrast microscopy was discovered a long time ago by Fritz Zernike. In fact, he got the Nobel Prize in 1953 for the development of phase contrast microscopy. But it was never possible to do this in the X-ray region. So one can do it in the visible, but in the X-rays has been very hard to set up because of the elements that the difficulty of the elements needed to do this. What is phase contrast radiography? Well, if we have an X-ray source on the left and you have the detector on the right, there are two ways to produce the image. You see here the X-rays in the vacuum. If X-rays are going in the vacuum, you don't have attenuation, and you have a fixed phase in the radiation. But if these X-rays go through an object, then you will have afterwards some attenuation, so the amplitude will be smaller on one side, but also the phase will change. So this is, you will see some shift in the phase, and this can be described with the refraction index, which is written here. It has a real and an imaginary part, and this imaginary part is responsible of the attenuation, but this one minus delta is responsible of the shift in the phase of the radiation. So that phase provides additional information. If we are able to extract it, it will provide information about the object. So refraction index can be written in this way, and it is an interesting observation to see that this delta may be as larger than beta as much as 1,000. So for example, in invasive ductal carcinoma, which is a specific kind of cancer, delta has 1,000, has a value 1,000 larger than beta. So if we are not able to extract information on this shift, we are losing a lot of information on tissue, which is invasive and can be very damaging to the health. So this is just an example of something that we have not been using and can be exploited. So that this phase contrast may improve diagnostics efficiency, in particular in small or in tubular structures. So this is particularly interesting in mammography, where you are willing to detect small granular calcium pieces, right? So there are many different ways to extract the information in the phase. There is one called interferometry with an array of crystals and the X-rays. There is also diffraction-enhanced imaging, which uses also some detector and some analyzers and monochromators here. And there is also a grating-based phase contrast, which uses a grating here in order to enhance the diffraction component of the radiation interacting with the sample. But the easiest of all of them is the inline phase contrast, which consists of just putting the detector far away from the sample. It's as simple as that. You just take the detector, which usually is very close to the sample, just put it away, and then you start to produce some phase images. This is an example of a phase contrast image of carbon fiber. This carbon fiber is used in many mechanical structures, and eventually, when used in cars or in bicycles, you are very interested in seeing that there are no bubbles, because these bubbles in the resin, they reduce a lot the strength of this matrix. So you see this image of carbon fiber on the left as obtained with phase contrast, and you see the image with absorption on the right. So you are not able to see the bubbles here, and you see these small structures by just using phase contrast technology. And this is industrial application, but if you look at a biopsy, you also see the difference in the two tissues. And this small structure that you see here is a small calcium piece that was introduced in there. And you see the absorption image, you see the phase contrast, and this is obtained with a smaller dose. This was obtained with 0.6 milligrays exposition, and this with 0.8. The relevance of this, you may say, well, I can see this piece anyway, but the interesting issue of this image is that you can see the surrounding tissue. So the surrounding tissue would have much more information about the characteristic of these structures. It will tell you if this is a carcinoma with a prognostic, bad or a good prognostic in his development. So what we are implementing in the lab is phase contrast inline. So we require a small focal spot, good coherence, and we place the detector far away from the sample and produces images with the two things together, the absorption and the phase contrast together combined in the same image. So it enhances the border of the object. So this is the array. We have a distance R1 and R2 from the object to the plate, to the detector. And what we will have is illustrated here. We have the wave coming, and then we have some reduction. We have some attenuation, small attenuation, but we will have also some phase shift once these X-rays go through the object. So this is to say that when these X-rays come to the object, in the borders, you will have some shifting in the wavefront, and these shifts in the wavefront, it will produce some interference, and this interference will be observed in the detector plane. This is the trick of phase contrast inline. This is our layout. We have our source. This is the X-ray tube. We have the sample here, and we place the detector there. We have some cooling for the X-ray tube here, and some of the devices that we use. And we define in here these distances. These distances R1 and R2 are important because they define what we call magnification. The magnification of the sample will be described by this quantity, depending on the distances that we place there. So there is a function. I will not go into this detail. There is a modulated transfer function that defines the performance of the whole array. It depends on the frequency of the radiation. This is the modulated transfer function in our array, but I will not discuss it. This is too technical to discuss here. Just want to say that we use one of the phantoms that are produced with nylon bars in order to optimize some of the parameters that we will use. If we want to know which magnification is the best in order to obtain a good image, then we need to see these bumps here, which are the result of the interference of the radiation in the borders of these nylon bars. So these spikes give you information on what is the optimal value for the magnification to obtain a good image. So this is the structure that we have in an absorption image, in which these spikes do not appear. And then you see how this phantom looks in the case of the phase contrast. So you start to have a much better definition of the structure, of the nylon structure, and then you see these spikes over there, which shows the effect of the phase contrast in here. And using these phantoms and using these pictures, you can optimize the value of M that will give you the best images. So I'll show you now some of the images that we play with. This is a cherry. You see the absorption, and you see the phase contrast on the right. And we have also images in which tubular structures and small detail is observed in contrast and not in the absorption image. So this is, for example, one insect obtained with the same tube, with the same detector, and so on, and compare with the array in which all these small details are observed. So once we have these phase contrast images, the next step is to process those images in appropriate way to extract all the information. I will not give you details of that. There is a number of steps to prepare the image to be afterwards analyzed with a specific algorithm to extract most of the information we can get from that image. This is just, for example, the first step, which is filtering and so on. We equalize the different histograms that one obtains for the different images and go through a step of preparation of the image to obtain a much better quality picture. So this is, for example, one of the images that we obtained from a database of mammographies. And you see here some worrisome structures inside. And once we apply some of the processing techniques, then you can see more clear inside what is there, some microcalcifications. But
just a simple subtraction.
This was, in this case, it was a filtering and not a subtraction, because we don't have, in this case, we don't have anything to subtract with. It was just some processing that is not the final process that I will show you now. So this is just some preparation of the image to apply an algorithm that will help us to extract more information about possible microcalcifications in the tissue. So what we propose is to process these images with what we call the Salis non-extensive entropy. And this is the part I would like to tell you now. There is an information theory, a definition of entropy for a picture, which is defined in this way. This is, you all know, the Boltzmann entropy, which is defined as a Boltzmann constant, the logarithms of the all the microstates in an array. But Shannon used this concept of entropy and give this definition, which is given by the sum of all the probabilities of each array for a system multiplied by the logarithms of all these microstates. In fact, in the information theory, people call this part the information, so that the Boltzmann-Shannon entropy can be written as the probability, sum of the probabilities times the information in the picture. If we take for each microstate an equal probability for all the states, then we get the maximum entropy that the system can obtain. And in the case of Shannon, the maximum entropy is given as this. This is the logarithms of the probability for each one of the states in the system. So, but this definition of the entropy is extensive. It is extensive in the sense that if you have a system of particles on the left and you have another system of particles on the right, if you put them together, this is additive. You can just add the two entropies, the entropy of the system on the left and the entropy of the system on the right, and the sum of these two will give you the entropy of the whole system. In that sense, the Boltzmann entropy is extensive. Now, there is a proposal of an entropy, which is called the Tsallis entropy, which is not extensive. And you find in nature many systems which are non-extensive. There are many, many areas in which entropy is related between the two sources, and you cannot just put them together. So this is why Tsallis is a physicist that proposed a new entropy, which is defined in this way, which is not extensive. If you add two systems, you have system A and system B, then the entropy of the two together will be not only the sum of the two entropies, but also there is a correlation, which is given by the value of Q, but some Q, which is give you the level of non-extensiveness of the entropy. So when one takes this entropy, you can get also the maximum value that it can take, and this is obtained when this, again, the probability of all the microstates is the same. And then this is the maximum entropy for the Tsallis entropy, right? So non-extensive entropy in the limit will give you the Boltzmann. If you take Q equal to 1, you will recover the Boltzmann entropy, as you would expect. And somehow this Q defines the degree of non-extensivity in the two systems. So that the entropy of Boltzmann-Shannon is, in general terms, special case for this Tsallis entropy. This entropy of Tsallis has been applied in many areas of physics. It's been very successfully used even to describe data in the Large Hadron Collider. It's used also in cosmology to describe the flux of cosmic rays of high energy that is coming from the universe. And it's been used in so many areas in a very successful way. So this is why this called to our attention to see if we take an image and we treat this picture as a two systems combination, the background on the one side and the object. So we have then two systems, A and B, and the two of them have different entropies, but they are not extensive in the sense that they are related. The background is related with the object. So we decided to treat the picture in terms of the Tsallis entropy and treat it as a non-extensive array. So the problem of using the Tsallis entropy is to determine the value of Q, because there is nothing that tells you what is the value of Q. It's very hard to work with this entropy because you don't know how the two systems are related. What is the level of non-extensivity on one side, or the level of correlation between the background in this case and the object, or between the two systems. So what we did with one of our students, our PhD students, is to think about the possibility to determine Q. And what we have done is to look at the maximum value that the entropy of a system may take. So let's define this entropy as S max, and then we know that the information contained in the system is the sum of the actual value of the entropy plus redundancy. So that the redundancy is written then in terms of the maximum value that the entropy may take for a system minus the actual entropy. And this is the same that written the normalized redundancy in this way. So the redundancy in the Shannon definition of entropy can be written as in this way: 1 minus the actual entropy divided by the maximum possible value of the entropy in the Shannon description, and in the case of Tsallis is the same. So redundancy does not have normally a real use, but we decided to maximize the redundancy, considering that it is very important to have a huge redundancy when you are going to transmit information. For example, if you have the Holy Scriptures and you need to keep intact this information across millennia, then you need that this that the stories that are written there have a big redundancy. So you can check parts of the scriptures and check that the information remained there. So this is just an example of why redundancy is important in language and communication and so on. So what we are proposing is to maximize redundancy in the images. So we take an image and plot the redundancy, for example, in this case, one of the radiographies that we obtain, and plot the redundancy with the Salis entropy versus Q. And you see that there is a point where there is a Q value here in which the redundancy is the maximum. So
you have Qs that are negative.
You may have negative Qs, I mean, in general terms. In the specific case of our arrays, you wouldn't have a negative Q because you're taking just background in the picture and the object. But in general terms, people may consider negative values of Q, depending on the physics behind the two systems. So you see here then the plot of one specific picture, and this is the plot that shows you how this redundancy changes with the Q value. And you can see that in this specific case, Q having the value of 0.7 will be the maximum redundancy. So this is the idea that we want to play. Find this maximum in the redundancy to get the Q value. And then afterwards, once we have this Q value, then go to the next step, which is the binarization of the image. The binarization is just to take a specific value for degree level in the image, and then all what is below this value will be treated as a white, and above this will be treated as a black. This is just to have in an image two values, 0 or 1. This is the final step in the treatment of the image, and for that we take again the two parts in the radiography. One is called A. We obtain the entropy of the object, for example. We obtain the entropy in the background, and we obtain the Q value in this way, optimizing for the redundancy, and then obtain the maximum value for this figure. This is the sum of the entropies. The entropy for the source, say the background, the entropy for the object, and then having the optimized value of Q, then the correlated part in the sum of the entropies. And these are particular examples. This is the all in its nest. This is an image that we just take from whatever, from the web. And this is the gray histogram for this image. And if we make the redundancy for this picture, just treating this image as a matrix and getting all the values, all the entropies of the background and the object, and plotting against Q, we obtain the maximum value of the redundancy. And in this particular case, for this picture, we obtain Q equal to 0.47. So this is the case of this image with this Q value. And once we binarize this image, we obtain the detail inside. And this is the same treatment, but with the Shannon entropy. In the case of Shannon entropy, it's just taking Q equal to 1, which is just one solved system. And you can compare the information that you end up with the two treatments in the two images. And one very famous picture in the treatment of images is Lina, this playmate from Playboy that is always used by the people that do these kind of things. And this is the gray histogram of Lina, and this is again the plot of the redundancy versus the Q value. In this case, the maximum is with Q.2. And again, this is the Salis processing with the Q.2. And once it is binarized, you see the information that it remains. And in this case, compared with the Shannon entropy. So you can see that there is quite a difference in the quality of the images. Of course, we do not pretend that this is the best you can do with the image. This is just a testing with some images that you can find anywhere to see if the value that we obtain with Q does better than just taking the traditional entropy. So we just want the comparison. It's not that we are we are not trying to convince you that this is a wonderful image. We just want you to convince you that if you compare the two procedures, then you get a much better information on the left than on the right. So I'm just about to finish. In conclusion, we have an urgent need to develop technologies in medical imaging, considering that there are new challenges in the health, in public health. There is a way to obtain phase contrast with a very easy array, but we are also, of course, considering the possibility to implement grating technology to extract the phase in the array. And then we have a method to estimate the appropriate entropy index in order to maximize redundancy and generate better segmentation images. So just to finish, this is the results that was obtained by this guy, is Abdiel, who did his PhD in this technique, and this is the publication that is the first part of the analysis, which gives you more detail. If you are interested in the whole procedure, it will give you more detail on how this was done. So this is one of the publications, and we are preparing now a similar analysis, but not with the picture that we take from the web, but with the pictures that we obtain with phase contrast in our array. So this will be the next step in this research project. And with this, I'm finished. Thank you very much.
Yeah, Barbara?
I have a question that's probably more about epidemiology than physics or optics. In one of your early slides, you showed what looked like a pretty strong gradient, geographic gradient in your country
Yeah.
of cancer rates. So the happiest reason I can think of for that is a change in reporting or diagnosis. But I'm sure people have looked at this. Is there some chance that the normalized rates are actually higher in the north than they are towards the south?
Yes, yeah, you are right. This has been discussed a lot in Mexico. And there are some people that say that it's simply that this region is richer and there are more mammographs there, that women are having screening, and then you, as a result, you are having more people with breast cancer. But some other people believe that that there are other factors. For example, in this region of the country, how do you say, the nutrition traditions are different. So people is closer to the United States in the way they consume than this one. This is more corn-based, how do you say, alimentación? Yes, right? And a different diet, that's right. So there are some discussions about this, and people considering this possibility and considering also a higher consume in artificial products and so on. But you see, Mexico City is also one of these, is in this region. And I believe that in general terms, this is increasing in the whole country. Another issue that has been discussed is there is now a study of the genetics of the population, and people find a stronger component of European population in the north than in the south. So this is more an indigenous population, and this is more European population. This has been obtained with an analysis of the country. So some people say this is also maybe a factor, that this is, the prevalence is much more important in European descendants people. So.
The reason you're using the Salis entropy is because you want to establish a good contrast with a background, correct?
Yeah, we believe that if you look at the image, you will have actually two components. One is the object that you want to see, and there is a background. And this, okay, you would say, okay, we have two sources, A and B. And probably the entropy of the two are completely independent, and then we can use the Boltzmann entropy. But maybe not. Maybe they are correlated somehow because, this is the same source of radiation and so on. And this is why we decided to go to the Tsali Center.
My question is, are there other entropies like relative entropy, Kullback-Leibler? Could you use Kullback-Leibler, for instance?
Not yet. So we started with this entropy that gives us the possibility of considering two systems. And then we are willing to explore other possible definitions, yes. Yeah. Michael?
The owl doesn't want to be found, right? So,
Yeah.
So you could imagine that the owl's feathers are designed not to be seen somehow. But the cancer doesn't know about your X-ray machine, right? So I'm just trying to get a physical feel about why this Salas entropy is useful both for finding the cancer and for finding the owl. Because
No, what we believe is that if you have a radiography like this, then I didn't go into all the details of the image treatment, but there is quite so many steps in doing this. And you have to separate first the object from the background. This is segmentation this is a step that we do. And then in this way, you separate the two systems. Now, how to know that in this structure there is that many detail, and that this detail can tell the physician information about the prognosis of this? Then the only possibility is to see the way to extract this information, and there are many factors. And we are planning to work in all of them. So we are planning to have a very nice X-ray tube with a small focal spot and so on, with coherence, a much better coherence and so on. And then going into the detector and have a much better detector, improve the resolution of the detector and so on. And then go into the new technique, which is this phase contrast, not absorption, not the traditional one, but using phase contrast, and then going into the algorithm and have a much better algorithm that considers the image nature, which is not necessarily one source, but two sources, which are non-extensive, and so on. So this is the project. So this is a long-term project that goes to all these aspects to produce a much better image. Yes.
Is the information about attenuation also used in addition to the phase contrast, or is it really unknown?
In our case, it's inevitable because with this array, you actually get the two components, right? So when you have this is our array. This is our array. We have the source, we have the object, we have the detector, and you have the two of them together. You have some attenuation. This is the intensity of the wave originally. You have the object, and in the end, you have some attenuation too, so you cannot separate. In principle, you will never be able to separate the two. The idea would have to have such a small attenuation here that all the effect in there is just phase contrast. Why this would be the ideal? It will be the ideal because if you don't have attenuation, it means that the dose that the patient receives is very small. So that you get a very nice image without irradiating the patient, right? So, but you will not be able to avoid it anyway. So you will have some attenuation, and the picture that you get here is together. You have the attenuation and the phase contrast together, right? Yeah.
Yeah, I have a quick question. I'm not sure if I'm seeing too much, but for example, the Q parameter in the Salas entropy, does it have contain any information about the nature of the system, or is it just a coupling parameter that tracks the two systems?
You know, the Q parameter of the Salas is a mystery. So for people that use this entropy in other processes, in other completely different processes in nature, in high energy physics, in particle physics, in cosmology, or whatever, it's really an issue to know what Q actually represents. In general terms, it's just the factor that gives you the level of correlation between the two systems somehow. if you want to have an idea of what is Q, is somehow the level of correlation between the two systems. And we believe this is why it is interesting to put it in the images, because we believe that somehow the object and the background must be correlated. You cannot separate them. So you will have a different background if the object were not there. So this is a natural. But what exactly is Q? What is the physical meaning of Q is something that is controversial. And before our work, as far as I know, maybe Michael knows, because experiments in the Large Hadron Collider have used this entropy and so on. And some other people is using Thales entropy for other things. But as far as I know, this is the first time that there is a concrete proposal to determine the value of Q. Otherwise, it will be done empirically. Just take one Q value and put it there and see if it is nice. Then you say, this is a nice fit to my data. But now we have a reason. We are using one Q because it maximizes the redundancy in the picture. This is the contribution of this work. So
I have one question. So what would be I think your idea of using a modified X-ray tube is because you mentioned in your colloquium that there are so many X tubes in the hospital and so on. So does it mean that your plan is to modify, to have a proposal to modify the X tubes in hospitals, and so that this can be used, this technique can be used, and so everywhere? And how feasible is that? Is that your idea?
You know, this fine focus tube, when we got it 15 years ago, was the top. But now it's terrible. I mean, there is fine focus. There is now X-ray tubes with obtained focal spots of nanometers. So this is microns. So but we don't have the money to get one of those nice X-ray tubes. So what we are trying to do is to improve our X-ray tube as much as we can. So because we don't have the money, this is very expensive thing. So when we bought this one, it was the most expensive X-ray tube in the market, but it was 15 years ago. So what we are trying to do is to use this because we have it and going down with the focal spot as much as we can, just looking at the voltages, currents, and changing. You can also change the angle of the target. If you change the angle of the target, then you have an effective smaller focal spot there. So the focal spot is actually the combination of the angle of the target and the focusing of the beam, the electron beam. So you play a little bit in order to improve your tube as much as you can. But in the market, you have better X-ray tubes. So now the idea will be to have the whole setup and then improve all you can improve. And eventually, if you go with this technique and a much better X-ray tube, then you will be much better on. So this is.
So thank you very much for your.
Thank you.